Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to discuss about the module Ensemble Theory, Classical Part 4, Canonical Ensemble, Idea of Partition Function and Applications under the paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We intend to appreciate the need to go beyond microcanonical ensemble in practical situations encountered in real physical problems. See that in canonical ensemble, we relax the energy constraint imposed in microcanonical ensemble to exchange energy with the surroundings, called heat bath at constant temperature. Understand the concept of statistical density function or statistical distribution function, rho as a function of Q, P and T, and link it to the ensemble average of a physical quantity and see its advantage over the equivalent time averaging. Derive the probability of finding a system with energy ER in two alternative ways. First, system plus heat reservoir approach. Second, method of most probable state using Lagrange's undetermined multipliers. Understand the key concept of a partition function, which implies partitioning of the members of the ensemble into a set of systems in different energy levels. Know interesting properties of the partition function as a function of macroscopic variables and link these to thermodynamic properties of the system. Know the concept of density of states and partition function in phase space. To apply the approach of canonical ensemble via partition function to look at some interesting physical systems to appreciate the effectiveness of the method. 2. A two-level system, classical ideal gas and Maxwellian distribution of speeds. This module has been developed for postgraduate level as per the following subtopics: canonical distribution function, system and heat bath approach, canonical distribution function, most probable value approach, idea of partition function and thermodynamics, degenerate energy levels, probability distribution and partition function, density of states and partition function in phase space, factorability of partition function, applications, a two-level system, a classical ideal gas, Maxwellian Boltzmann distribution of speeds. In the last module, we studied the microcanonical ensemble, which was a highly constrained way of looking at macroscopic systems. Practically not possible to achieve because nothing can be completely isolated as envisaged in it. To have a more practical approach, instead of energy, which is not only difficult to keep fixed, temperature is a better thermodynamical variable which can be controlled and measured easily. For this, the macroscopic system can be put in a heat bath with infinitely large heat capacity and allowed exchange of energy to keep temperature constant. Such a macroscopic system is described by the parameters N, V and T, and the corresponding ensemble is called canonical ensemble. In this ensemble, the energy of the system is allowed to vary between 0 to infinity. We are interested in asking the question, what is the probability PR that the macroscopic system in the ensemble is in one of the states described by energy ER at any given instant of time? The concern in this module is to answer this question, derive canonical distribution function and learn how this approach can be applied to some prototype models. canonical distribution function, system, and heat bath approach. To answer the question raised in the beginning, we start by following an approach called system and heat bath approach. We take our system designated A and put it in a heat bath designated as A dash, such that system and the heat bath designated A total is equal to A plus A dash in the figure 1 are allowed to exchange energy, keeping system and heat bath in equilibrium at a common temperature T. Heat bath is very large, having a large heat capacity. The composite system AT together is completely isolated such that if at any time system A has energy ER and heat bath A dash having energy ER dash, then the total energy ET is constant. That is, ER plus ER dash is equal to E total is equal to constant. Since heat bath is very large, ER is very much less than ET. That is, ER upon ET is equal to 1 minus ER dash upon ET, which is very much less than 1. Since the heat bath is very large, the number of states compatible to it with energy E dash R represented by omega dash as a function of ER dash is very large and is independent of the nature of the reservoir. It is worth noting that larger the number of states available to the reservoir, larger is the probability of it assuming energy ER dash, and consequently the system immersed in heat bath assuming energy ER. As per the principle of equal a priori probability, different microstates in the reservoir are equally likely to occur. The probability of system A occurring with energy ER, denoted by PR, is proportional to the number of microstates which the reservoir has, that is, omega dash as a function of ER dash. Therefore, PR is proportional to omega dash ER dash and is equivalent to omega dash as a function of E total minus ER. Noting inequality 2, we can expand the right hand side around ER dash is equal to ET, which means around ER is equal to 0. Recalling that omega dash is a very large number which varies very rapidly, it is therefore more convenient to deal with logarithm of this function, which is a slowly varying function. So, log to the base E of omega dash as a function of ER dash is equal to log of omega dash as a function of E total plus partial derivative of log of omega dash with respect to E dash evaluated at E dash R is equal to ET multiplied by E dash R minus ET plus so on gives log of omega dash ER dash is approximately equal to log of omega dash as a function of ET plus partial derivative of log of omega dash with respect to E dash evaluated at E dash R is equal to ET multiplied by minus ER plus so on. Recalling, derivative of log of omega dash with respect to E dash is equal to beta dash is equal to 1 upon kbt dash, and at equilibrium beta dash is equal to 1 upon kb t dash is equal to beta is equal to 1 upon kbt. Equation 5 can be written as log of omega dash as a function of ER dash is approximately equal to constant minus beta ER. From third and sixth, we get PR proportional to e raised to power minus beta ER. Since sum of all probabilities must sum to 1, normalizing 7, we get PR is equal to e raised to power minus beta ER divided by summation over R e raised to power minus beta ER, where summation is over all state which system A can take. Equation 8 is the canonical distribution function which provides the probability of the system in state with energy ER. Furthermore, since equation 8 has been derived by using very fundamental ideas of physics involving conservation of energy, extensiveness of energy, E total is equal to ER plus ER dash, slow and smooth variation of log of omega E, independent of the choice of quantum mechanics or classical mechanics, it is applicable very generally, as we shall see later in applications. Canonical distribution function, most probable value approach. We consider an ensemble of n identical systems which are allowed to share energy curly E. Let ER, R is equal to 0, 1, 2, 3 denote the energy eigenvalues of the system. If NR denotes the number of systems which are at any instant having the energy value ER, then NR and ER together satisfy the following two conditions. Summation over R NR is equal to capital N, and summation over R NR multiplied by ER is equal to curly E. Any set of values of NR which satisfy conditions stated in equations 9 and 10 is a possible way of distributing total energy curly E among n members of the ensemble. There are a number of ways of distributing this total energy E among the members of the ensemble, giving different distinct states. These different ways can be counted, denoted by a very special symbol W over a set of NR, given by WNR is equal to n factorial divided by n0 factorial, n1 factorial, n2 factorial, and so on. According to the principle of equal a priori probability, all possible distribution of energy among members of the ensemble are equally likely. The frequency of achieving a given set NR is directly proportional to the number W over a set of NR. Out of all these sets, the most probable set shall be the one for which W over a set of NR is maximum. Once we have identified this set, say N star R, we shall be physically interested in this distribution. However, statistically, we cannot ignore other NR dash sets with their corresponding weights or frequencies to calculate the expectation values or mean values of the numbers NR as given here. Curly bracket NR, curly bracket closed, is equal to summation over the set NR dash NR multiplied by WNR divided by summation over NR dash WNR. Significance of N star R lies in the fact that the fraction N star R divided by capital N is the canonical probability PR. Let us now calculate the desirable numbers over a set of NR star and the mean value NR. Again, for the reasons stated earlier, log of W is a slowly varying function and we shall use it to proceed further, which implies log of W is equal to log of n factorial minus summation over R log of NR factorial. In thermodynamic limit, applying Stirling's formula, equation 13 becomes log of W is equal to n log of n minus summation over R NR log of NR plus summation over R NR. Since summation over R NR is equal to capital N, this simplifies to n log of n minus summation over R NR log of NR. If NR changes by a small amount, log of W changes by a small amount also, which can be written as delta log of W is equal to summation over R log of NR plus 1 multiplied by delta NR. Now for NR to be maximum, delta log of W should become 0. provided equations 9 and 10 also satisfy the following conditions simultaneously. That is, summation over R delta n R is equal to 0 and summation over R ER delta n R is equal to 0. Now to get the set n star R, method of Lagrange's undetermined multiplier can be used, according to which equations 15th, 16th and 17th together yield the condition summation over R bracket minus log of nr plus 1 minus alpha minus beta ER bracket closed delta nr is equal to 0, where alpha and beta are Lagrange's undetermined multipliers. Since delta nr is completely arbitrary, for equation 18 to be satisfied, its coefficients must become 0. That is, for all r, minus log of nr star plus 1 minus alpha minus beta ER equals 0, or log of nr star is equal to 1 minus alpha minus beta ER, or n star r is equal to e raised to power minus 1 plus alpha multiplied by e raised to power minus beta ER, which is equal to a constant multiplied by e raised to power minus beta ER, where now the constant c and beta are two undetermined parameters, and equation 21 gives us the most probable distribution. To calculate c, we note summation over nr star is equal to capital N is equal to c multiplied by summation over r e raised to power minus beta ER, or c is equal to capital N divided by summation over r e raised to power minus beta ER. Therefore, PR is equal to nr star divided by n is equal to e raised to power minus beta ER divided by summation over r e raised to power minus beta ER. Now, the other Lagrange's parameter beta can be obtained from a solution of the equation mean value of E is equal to summation over r ER e raised to power minus beta ER divided by summation over r e raised to power minus beta ER, which can be written equal to minus partial derivative of log of summation over r e raised to power minus beta ER with respect to beta. According to statistical mechanics, the mean value of energy is thermodynamic energy E. Furthermore, P is equal to negative of delta ER divided by delta V, that is partial derivative of ER with respect to V. Therefore, average value of P is equal to minus summation over R delta ER over delta V multiplied by e raised to power minus beta ER divided by summation over R e raised to power minus beta ER. Here, mean value of P corresponds to thermodynamic pressure. Let us differentiate equation 25 with respect to V, remembering that ER is a function of capital N, V and beta. Keeping capital N and beta fixed, we have partial derivative of mean value of E with respect to V at constant N and beta is equal to negative of the mean value of P plus beta times the mean value of EP minus beta times the mean value of E multiplied by the mean value of P. Now we can differentiate equation 26 with respect to beta. We have partial derivative of mean value of E with respect to beta at constant N and V is equal to mean value of E multiplied by P mean value minus mean value of EP together. Multiplying 28th on both sides by beta and adding to equation 27, we get partial derivative of mean value of E with respect to V at constant N and beta plus beta times partial derivative of mean value of P with respect to beta at constant N and constant V equal to negative of the mean value of P. Let us compare equation 29 with the well-known thermodynamic relation partial derivative of V with respect to V at constant t and n minus t times partial derivative of P with respect to t at constant n and V is equal to partial derivative of E with respect to V at constant t and n plus 1 upon t partial derivative of P with respect to 1 upon t at constant n and constant V is equal to minus P. One can easily conclude that beta is equal to constant divided by t is equal to 1 upon kBt, where kb is well-known Boltzmann constant. Idea of partition function. Equation 8 and 24 derived above represent the canonical distribution function. PR is equal to e raised to power minus beta ER divided by summation over R e raised to power minus beta ER. It has a very interesting feature worth mentioning, which is clear from the graph of PR versus ER shown in figure 2. As the energy of the state ER increases, its probability decreases exponentially compared to low energy states, clearly showing that probability distribution is not uniform, unlike in microcanonical case, where it is uniform with all states having equal probability. The denominator in canonical distribution function, conventionally represented by z, that is, z is equal to summation over r e raised to power minus beta er, is called the canonical partition function or canonical sum over the states. It is obviously a function of t and via er a function of n and v, that is, z is a function of n, v and t. The partition function can be a function of any other parameter on which ER depends. Knowledge of partition function is the most important result of the statistical mechanics, since once it is known, then all equilibrium physical properties of the macroscopic system under consideration can be known from it. Nobel laureate Richard Feynman, in his book on statistical mechanics, described partition function as the summit of statistical mechanics. He expressed this in the following words, and I quote, "Entire subject is either the slide down from the summit, as the principle is applied to various cases, or climb up to where the fundamental law is derived and the concept of thermal equilibrium and temperature T are clarified." Partition function in thermodynamics. Average energy of the thermodynamic system. Let us look at the equation 25, which represents average energy written in canonical ensemble. It can be written in terms of partition function as mean value of energy is equal to negative of partial derivative of log of summation over r e raised to power minus beta er with respect to beta is equal to minus partial derivative of log of z with respect to beta is equal to minus 1 upon z partial derivative of z with respect to beta. This further provides us a way to calculate the specific heat in terms of z. Average pressure and average of other generalized forces. We know in general that a thermodynamic system under consideration has number of external parameters, symbolically written as capital X1, capital X2, capital X3, so on up to capital Xk. If such an external parameter is changed by an infinitesimal amount from xi to xi plus dxi, this causes a change in its energy as d is equal to summation over I partial derivative of E with respect to xi dxi. Here, dE is the amount of work done by the generalized force Fi is equal to partial derivative of E with respect to xi. Now, if we recall V as an external parameter, the generalized force corresponding to that is pressure. P is equal to minus partial derivative of E with respect to V. The average of pressure can then be written as equal to summation over R partial derivative of ER with respect V e raised to power minus beta ER divided by summation over R e raised to power minus beta ER, which is equal to 1 upon beta partial derivative of log of Z with respect to V, that is volume. Thus, average of the generalized force F for the external parameter X can be written as average of F is equal to summation over R partial derivative of ER with respect to X e raised to power minus beta ER divided by summation over R e raised to power minus beta ER is equal to 1 upon beta multiplied by partial derivative of log of Z with respect to X. Entropy. Partition function of Z is a function of V and T. That is, Z is equal to Z, which depends on V and T, or of V and beta. That is, Z is equal to Z as a function of V and beta. Thus, the differential of log of Z is equal to partial derivative of log of Z with respect to beta multiplied by d beta plus partial derivative of log of Z with respect to V multiplied by dV. Please remember that Z here corresponds to partition function. Using equation 31 and 33, we have total differential of log of Z is equal to minus E d beta plus beta times P dV plus beta times dE minus beta times dE, or full differential of log of partition function is equal to minus differential of E beta plus beta times P dV plus beta times dE, or the full differential of log of partition function plus E beta is equal to beta P dV plus beta dE, which is equal to 1 upon kb multiplied by P upon T dV plus 1 upon T dE. Since P upon T dV plus 1 upon T dE is equal to ds, we have S is equal to kb log of partition function plus E beta. Helmholtz free energy F. We know Helmholtz free energy is given by F is equal to E minus Ts. Using equation 39, we have F is equal to E minus Tkb log of Z plus E beta, which is equal to minus kb T log of Z, where Z is the partition function. Degenerate energy levels, probability distribution, and partition function. In actual physical systems, there is high degree of degeneracy with a set of states GR, a number called degeneracy, having same energy ER. It is expected that these GR states are equally likely to occur, and probability is scaled up by the degeneracy GR of the state ER. In such a case, equation 8 for the probability of the system to be in the state ER becomes PR is equal to GR e raised to power minus beta ER divided by summation over R GR e raised to power minus beta ER. Now we will look at a very useful concept called density of states. We must remember that in a macroscopic system, the energy levels EI of the system are bunched together very closely. One finds that in such a case, in a small interval dE of energy around E, a very large number of energy levels lie, forming almost a continuum. Therefore, E can be treated as a continuous variable and define PDE as a probability that the system of the canonical ensemble has the energy in the interval dE around E, which is proportional to single state probability e raised to power minus beta E multiplied by number of energy states GE lying in the interval dE, where G as a function of E is called density of states. Thus, PEDE is proportional to e raised to power minus beta E GE, that is density of states, multiplied by the energy interval dE. On normalization, this becomes PE dE is equal to e raised to power minus beta E GE dE divided by integral from 0 to infinity e raised to power minus beta E GE dE. The partition function in this case becomes Z beta is equal to integral from 0 to infinity e raised to power minus beta E GE dE. It is worth noting here that partition function as a function of beta is the Laplace transform of density of states GE, and the Laplace transform can be inverted to give the density of states. GE is equal to 1 upon 2 pi I integral from beta dash minus iota infinity to beta dash plus iota infinity of partition function multiplied by e raised to power beta E d beta, where beta dash is greater than 0. The expression for the average value of a physical quantity f can be written as then average value of f is equal to integral from 0 to infinity f e raised to power minus beta E GE dE divided by integral from 0 to infinity e raised to power minus beta E GE dE. Partition function in phase space. For the sake of completeness, it is worth mentioning here that the formalism developed above can be applied to both classical as well as quantum mechanical systems. In the case of classical system, this formalism can be expressed in the language of phase space. Let us recall the definition of ensemble average encountered in the module earlier. That is, ensemble average of the physical quantity f is equal to integral over rho qp, that is statistical distribution function, multiplied by physical quantity f as a function of p and q integrated over d3 and q, d3 and p, divided by integral of statistical distribution function rho, which is a function of q and p, over d3 and q, d3 and p. Here, rho qp is the phase space density telling us the probability of finding a representative point near qp, which ultimately depends on the Hamiltonian h qp of the system. In canonical ensemble, therefore, rho pq is proportional to e raised to power minus beta hqp. Thus, 47 becomes ensemble average of f is equal to integral of e raised to power minus beta h as a function of qp multiplied by f as a function of qp integrated over d3 and q and d3 and p, divided by integral of e raised to power minus beta hqp over d3 and q, d3 and p. Once again, we note that the denominator is related to the partition function, provided phase space volume is suitably modified by replacing the factor d3 and q multiplied by d3 and p by d3 and q into d3 and p divided by n factorial multiplied by h raised to power 3n, enumerating the distinct number of quantum states. Therefore, partition function for the classical system is z n as a function of v and t is equal to 1 upon n factorial h raised to power 3n integrated over e raised to power minus beta h as a function of qp integrated over d3 and q, d3 and p, with integration extending over the whole phase space. Factorability of partition function. Let us note another significant property of the partition function called factorability in the case of non-interacting systems with no quantum correlations. Let us take a system of n independent non-interacting entities, for example, atoms or molecules in an ideal gas, or small vibrational modes in a solid such as phonemes, etc., such that Hamiltonian of such a system can be written as H is equal to summation over I Hi, where Hi is the Hamiltonian for a single entity of the system. So the partition function of the system as given in equation 50 becomes partition function is equal to 1 upon h raised to power 3n n factorial integral of e raised to power minus beta summation over I hi qi pi multiplied by the product from I is equal to 1 to n d3 qi d3 pi, or Zn Vt is equal to 1 upon n factorial, square bracket begins 1 upon h cube integral of e raised to power minus beta hi qi pi multiplied by d3 qi d3 pi, square bracket closed, bracket raised to power n, which is equal to 1 upon n factorial multiplied by z1 as a function of v and t raised to power n, where z1 as a function of v and t is equal to 1 upon h cube multiplied by integral of e raised to power minus beta hi as a function of qi pi integrated over d3 qi d3 pi. Result 53 represents the factorability of the partition function for non-interacting entities in a system. This conclusion remains valid for non-interacting entities even when the entities have internal degrees of motion. Applications: a two-label system. The single particle partition function can be written as Z1 is equal to e raised to power 0, that is 1, plus e raised to power minus epsilon, so that total partition function can be written as Z is equal to 1 plus e raised to power minus beta epsilon whole raised to power n. Using the relation of thermodynamic quantities, we can get Helmholtz free energy as F is equal to minus 1 upon beta log of Z, which is equal to minus n upon beta log of 1 plus e raised to power minus beta epsilon, which is equal to minus n kbt log of 1 plus e raised to power minus epsilon upon kbt. Internal energy E is given as E is equal to minus 1 upon Z, partial derivative of Z with respect to beta is equal to n epsilon divided by 1 plus e raised to power beta epsilon. Entropy can be obtained as follows: S is equal to Kb log of Z plus E beta, which is equal to n Kb log of 1 plus e raised to power epsilon by kbt plus epsilon by kbt divided by 1 plus e raised to power epsilon by kbt. Classical ideal gas. In Module 8, we discussed at length classical ideal gas from statistical mechanics route. Here we shall revisit this from the point of view of canonical ensemble. A classical ideal gas is a system of n identical monoatomic molecules confined in a volume V at temperature T with no interaction among the molecules. Hamiltonian of such a system is merely a sum of kinetic energies of each molecule, which can be written as H as a function of Q and P is equal to summation over I is equal to 1 to n pi square divided by 2m. Using 53, partition function can be further written as equal to 1 upon n factorial, square bracket begins, 1 upon h cube integral of e raised to power minus beta p square by 2m d cube q d cube p square bracket closed raised to power n, or partition function is equal to 1 upon n factorial, square bracket begins 1 upon h cube integral over d3q multiplied by integral of 0 to infinity e raised to power minus beta p square by 2m d cube p square bracket closed raised to power n. First integral in the above equation is over space coordinates giving v raised to power n, giving the partition function is equal to v raised to power n divided by n factorial h raised to power 3n square bracket begins integral from 0 to infinity e raised to power minus beta p square by 2m d cube p square bracket closed raised to power n. Equation 63 can be further simplified by expanding in polar coordinates to give partition function is equal to v raised to power n divided by n factorial h raised to power 3n square bracket begins integral from 0 to infinity e raised to power minus p square by 2m kbt 4p square dp square bracket closed raised to power n. Using the standard integral from 0 to infinity e raised to power minus alpha x square multiplied by x square dx is equal to 1 upon 4 pi upon alpha cube raised to power 1 by 2. We get partition function is equal to 1 upon n factorial v upon h cube 2 pi m kbt raised to power 3 by 2 whole raised to power n. Now we are ready to obtain thermodynamic functions using Stirling's formula. Helmholtz free energy is given as F is equal to minus kBT log of the partition function obtained is equal to n kBT within the square bracket log of n upon V h square by 2 pi m kBT raised to power 3 by 2 minus 1. Once we have F, all other thermodynamic properties can be derived immediately. For example, pressure P is equal to minus partial derivative of F with respect to V at constant n and t is equal to n kBT divided by V. This equation is nothing but the equation of state of an ideal gas. Chemical potential mu is equal to partial derivative of F with respect to n at constant V and constant t is equal to kBT log of n upon V multiplied by h square upon 2 pi m kBT raised to power 3 by 2. Entropy S is equal to negative of partial derivative of F with respect to temperature at constant n and V is equal to n kB log of V upon n h square upon 2 pi m kBT raised to power 3 by 2 plus 5 upon 2. Internal energy can then be written as, because we know E is equal to F plus Ts, using 66 and 69 to obtain E is equal to 3 by 2 n kBT. One of the very interesting applications of canonical distribution in classical physical systems is to obtain the distribution of velocities in a gas of an ideal gas. The aim of Maxwell-Boltzmann distribution is to find the number of molecules in the phase space volume d cube r d cube p around the representative point Rp as shown in the adjoining figure 4. The total energy of the gas consisting of n molecules in volume V is E is equal to summation over I is equal to 1 to n p square by 2m. The probability that molecule of the gas has velocity lying between V and V plus dV is given by the canonical distribution and is PRV d cube r dqv is equal to constant multiplied by e raised to power minus mv square by 2 kBT d cube r dqv. To get the Maxwell-Boltzmann distribution, let f r v d cube r dqv be the mean number of particles in the velocity space volume d cube r dqv, where frv is the velocity distribution. This number is also proportional to PRV d cube r dqv, that is FRV d cube r dqv is equal to a constant multiplied by e raised to power minus mv square by 2 kBT d cube r dqv. This number, when integrated over whole velocity space volume, is equal to the total number of particles. Thus, a constant multiplied by a double integral over r and v of e raised to power minus mv square by 2 kBt must be equal to capital N, or constant is equal to capital N divided by integral over d cube r multiplied by e raised to power minus mv square by 2 kBt d cube v, which is equal to n upon v multiplied by e raised to power minus mv square by 2 kBt 4 pi v square dv. Therefore, constant is equal to n upon v multiplied by m upon 2 pi kBt raised to power 3 by 2, or FRV, which is the velocity distribution, is equal to n upon v multiplied by m upon 2 pi kBt raised to power 3 by 2 e raised to power minus mv square by 2 kBt. Here we note that because of the isotropic nature of the system, FRV is independent of position, so that FRV is equal to FV is equivalent to FV scalar. To find the number of molecules in the range V and V plus dV, we multiply Fv with the volume of the velocity shell in the velocity space, that is 4 pi v square dv. Thus we get 4 pi v square Fv dv is equal to 4 pi n m upon 2 pi kBt raised to power 3 by 2 v square e raised to power minus mv square upon 2 kBt dV. The adjoining figure 5 shows the Maxwell-Boltzmann distribution for speed of molecules in an ideal gas against 2 kBt by m raised to power half v square. Similarly, figure 6 here shows that most of the molecules of an ideal gas have speed around a value which is dependent on temperature. The most probable speed can be obtained by taking derivative of Fv with respect to v and equating it to 0. This gives Vmax is equal to square root of 2 kBt upon m. Mean velocity of the gas is 0, since as many molecules move in the direction of positive axis as in the direction of negative axis. However, we can find out average speed V bar and root mean square speed Vrms. Average speed V is equal to 1 upon n integral from 0 to infinity Vfv dV is equal to 4 pi m upon 2 pi kBt raised to power 3 by 2 integral from 0 to infinity V cube e raised to power mv square by 2 kBt mv. Putting mv square by 2 kBt is equal to zeta square, such that V dV is equal to d zeta d zeta divided by m upon 2 kBt. We have mean value of V is equal to 4 pi multiplied by m upon 2 pi kBt raised to power 3 by 2 multiplied by 2 kBt by m raised to power 2 integration from 0 to infinity xi cube e raised to power minus xi square dxi. The integral appearing above is a standard integral such that integral from 0 to infinity xi cube e raised to power minus alpha xi square dxi is equal to 1 upon 2 alpha square. Therefore, we have the mean velocity is equal to square root of 8 upon pi kBt divided by m. Now the root mean square speed Vrms can be obtained, which is calculated as equal to 1 upon n square root of infinity v square Fv dv, which can be further written as 4 pi multiplied by m upon 2 pi kBt raised to power 3 by 2 multiplied by 2 kBt upon m raised to power 5 by 2 integral from 0 to infinity of xi raised to power 4 e raised to power minus xi square dxi. The integral appearing above is a standard integral such that integral from 0 to infinity xi raised to power 4 multiplied by e raised to power minus alpha xi square
dxi is equal to 3 by 8 multiplied by pi upon alpha raised to power 5 raised to power 1 by 2. Therefore, we have mean value of v square or the root mean square value is equal to 3 kbt divided by m. Thus, Vrms is equal to square root of 3 kbt divided by m. Here are some interesting conclusions. Each of these three velocities are proportional to square root of t, thereby implying that these increase as temperature T increases. V maximum is greater than V mean is greater than Vrms and are in the ratio of square root of 2 is to square root of 8 upon pi is to square root of 3.
So students, let us summarize what we have learnt in this module. In this module, we have learnt that canonical ensemble corresponds to a collection of exact replicas of a system where energy can be exchanged among the systems with temperature is equal to constant, number of particles n is equal to constant, and volume V is equal to constant. We saw the application of system heat path approach and method of most probable values via Lagrange's undetermined multipliers to derive canonical distribution function for a system given by PR is equal to e raised to power minus beta ER divided by summation over R e raised to power minus beta ER for a system with non-degenerate energy levels, and PR is equal to GR e raised to power minus beta ER divided by summation over R GR e raised to power minus beta ER for a system with levels ER of degeneracy GR each. That partition function is the key concept in statistical mechanics from which all the thermodynamic properties can be derived. The canonical partition function can be written as, for a quantum mechanical non-degenerate system, partition function z is equal to summation over R e raised to power minus beta ER. For a quantum mechanical degenerate system, z is equal to summation over R GR e raised to power minus beta ER. Quantum mechanical system with density of states GE, z beta is equal to integral from 0 to infinity e raised to power minus beta E GE dE. And for a classical system in phase space, partition function Zn as a function of V and T is equal to 1 upon n factorial h raised to power 3n integral over e raised to power minus beta h qp over the whole phase space. That partition function of non-interacting systems without quantum correlations is factorable. That is, partition function can be written as equal to 1 upon n factorial multiplied by 1 upon h cube integral of e raised to power minus beta hi qi pi over the whole phase space raised to power n, which is equal to 1 upon n factorial multiplied by single particle wave function raised to power n. That partition function of non-interacting systems without quantum correlations gives us interesting thermodynamic properties. For example, average energy E is equal to minus partial derivative of log of partition function with respect to beta is equal to minus 1 upon partition function multiplied by partial derivative of partition function with respect to beta. Average pressure is equal to summation over R partial derivative of ER with respect to volume multiplied by e raised to power minus beta ER divided by summation over R e raised to power minus beta ER, which in turn is equal to 1 upon beta partial derivative of log of partition function with respect to volume, and generalized force F is equal to summation over R partial derivative of ER with respect to x e raised to power minus beta er divided by summation over r e raised to power minus beta er is equal to 1 upon beta partial derivative of log of partition function with respect to x. Entropy S is equal to kb multiplied by log of the partition function plus E beta, and Helmholtz free energy is equal to minus kb T log of Z. We also learnt how to derive Maxwell-Boltzmann distribution of speeds and calculate maximum speed, mean speed, and root mean square speed. We obtained for Maxwell-Boltzmann distribution of speeds Fv is equal to n upon v multiplied by m upon 2 pi kbt raised to power 3 by 2 e raised to power minus mv square by 2 kbt. Maximum speed Vmax is equal to square root of 2 kbt upon m. Mean speed is equal to square root of 8 kbt upon pi m. And root mean square speed Vrms is equal to square root of 3 kbt upon m. Thank you.